final aside for this lecture is on space complexity. And for space complexity, I just want you to know that this is very similar to the runtime complexity we've been thinking about. We can analyze the space complexity by looking at how much additional space a program uses when it runs, or a function uses when it runs. And what takes up space? Well, creating variables takes up space. And then depending on the kind of type that you have, lists take up more space the more items you have in the list. Same thing for dictionaries. And same thing for sets, which you'll learn about soon, as well as tuples. But for time complexity, we picked this arbitrary unit of operations. It's kind of similar for space complexity. We pick some arbitrary unit of like some unit that we write to memory. Like an integer is 1 unit, a Boolean is 1 unit. Sometimes a string is 1 unit. Other times we think of a character as 1 unit. But it's important to point out that a list is many units. Like however many items are in the list, that is how many kind of new things you're creating in memory. And so we talk about space complexity just the same way as we did with time complexity, big O. You could try to measure using some sort of library or module in Python that measures how much space your program uses. That's possible. There are programs that do that. You run into the same problems that we talked about before, where it'll depend on which device you're running on and how it stores memory. You could just count the number of operations, storage operations, but also same concerns as before. And so we use the same exact thing, big O. And here, creating 2 integers in memory. So regardless of the size of n, we have constant space complexity. What about in this example? So here, mystery 1 takes and first it saves the length of nums into a new variable called length, and it creates a new list that's empty here. And for num and nums, it'll append in the worst case. Notice, in the best case, if the number in nums is equal to the item that's passed in, we stop. But in the worst case, item doesn't exist in nums, and so we just keep adding items one by one to the list until we copy the entire list. And so in the worst case here, we create a whole new list with n items in it, where n is the length of nums. And we also created this length variable up here. And so n plus 1 kind of units of memory were used. And big O of n plus 1, well, n is a higher order term, and so we keep just that. We drop the 1, and we get big O of n. So this is linear space complexity. If you're creating a new list that might have as many items, or at least half as many, or twice as many, whatever in terms of n, you have linear space complexity. We're going to talk about complexity, space complexity, and time complexity much more in class and in lab this week. We'll get to try some more examples. But with that, congratulations, you now know about how complexity works and big O and orders of growth, which will be the mathiest topic that we talk about this semester.